Hello, hello, everyone. I know, low energy. Getting towards the end of the meeting, getting towards the end of the semester. Everyone's sleepy, tired. But I urge you to, if I can steal your attention for the next 20 minutes, maybe. Is actually a really interesting topic that not a lot of people get into, in their time here. Trusted computing and how we actually secure like the hardware and the protocols that we use on the daily. We can focus on the application layer all day long. We can focus on securing our software vulnerabilities, this and that. But at the end of the day, we need to trust something, and we'll go over that. But this talks a little bit about the foundations behind, trust in computing and how we can apply those concepts to protecting online payments. So most of you know me already. It's not updating very fast or at all. Chase, you told me it was flawless. Oh, there you go. It's because I had it full screen on the other hand. All right. Yeah, running Fedora is not the optimal experience with Zoom, okay? All right, so most of you know me already, but hi, my name is Bradley. Some people call me Brad. Most people call me Brad. I'm from Richmond, Virginia. Is anybody else in here from Virginia? Well, I know Guido. Where are you from? Ashburn? Okay. Yeah. All right, cool. Yeah, all the people, from Virginia know where each other live. That's just how it is, you got that sixth sense. I got two cats, Dumpling and Uni. Go check out the cats channel. There they are too. Real cute, real sleepy. But I'm a fifth year computing security BSMS student. I'm old. I'm on my way out. I got 4 more weeks to graduate, hopefully. I'm also a CyberCore SFS scholar. So if you're interested in government work, scholarships, that kind of stuff, come talk to me. We can talk about it. I was the president of RITSEC, not this year, but last year. Felt like forever ago. Felt like forever during. But, so this isn't my first rodeo. Still a big Golang enjoyer, although this has changed since my last presentation. I had to update this. I am pursuing Rust a little bit. I still would consider myself a Rust baby, but going through the Rustlings course, it's real fun. But my favorite topics are pen testing, embedded systems, DevSecOps, software development. Honestly, anything as long as it's cool and you kind of pitch it to me and it sounds really cool, I'll get really excited about it and I'll want to spend the next 2 months working on it just because. You can nerd snipe me real easy. So that I don't have to interrupt my flow later, if you guys are interested now, you can scan this little fancy QR code. This will bring you to all of the source code that was developed for this project. Specifically, most of it's just proof of concept source code written in Go. So if you're a Go person, you can definitely understand that. So first, let's talk a little bit about trust. What is trust? Does anyone want to try their hand at defining trust? In general, doesn't have to be computers. Oh, something you have in me. Okay, I thank you. Thank you for trusting me. Anyone else have a very general definition for trust? No? All right, cool. Well, I looked it up because honestly, I didn't really have a general definition for trust. Apparently, it's the firm belief in the reliability, truth, ability, or strength of someone or something. So, all very good qualities of me, Connor would know, clearly. But obviously, this is super general, so let's apply it to kind of an example so that you can get a concept. So in this example, we have 3 people, and here's the pre-existing trust relationships. Let's say I am this person and Connor's that person, so Connor trusts me, right? Yep, already said that. And if now I trust the person in the middle, this is like the pre-existing trust relationship. And the question is, how does Connor know to trust this person? They want to know, is this person trustworthy? So the first step they're going to do is they're going to find someone that they trust, and they're going to go ask them, hey, do you trust this person? And they'll give a response, yes or no. If they trust this person, then I'm going to go ahead and trust this person because I already know that this person's trustworthy, so I'm going to trust that their decision is right. And in the real world, this could be a situation where this is the one person that everyone trusts. And if everyone in the world trusts this one person, that makes this person what we call the root of trust. Now, remember that terminology for later. Store it in your little brain database there. Hang on to that. We'll come back to it. So in the real world, these aren't people going around asking, do you trust this person? Do you trust this person? In the computing world, this gets replaced with servers and certificate authorities. Who knows what a certificate authority is? Raise your hand. Have you heard? Who has heard the word certificate authority or CA? All right, a lot more hands. All right. If you ever debug the browser, you're like, oh, why does it say not secure? Why is this little red thing up here? Yeah, certificate authority is super important. These are the roots of trust of our entire computing environment. These are the people that we're going to say that everyone in the world, we'll get to it, trusts. So they are a root of trust in this environment. And the people we're asking asking the certificates authorities about are these servers that we're connecting to. So this could be your browser, this could be anything. They'll have certificates, and we'll want to know, are they trustworthy? We can go ask their certificate authority who issued that certificate, saying that they trust this server. Do you trust this person? They'll say yes, and now we inherently trust that website or server or whatever. All right, switching gears a little bit. Digital signatures. Who has heard of a digital signature before? All right, medium amount of hands, okay. Does anyone want to give it a shot? Digital signature, one sentence explanation. That's good, yeah. Something that is digitally written to a file to show its authenticity. You're pretty much spot on, right? This is concerning how do we know that a file is the real file and it wasn't modified? How do we know it's authentic? So in general, let's generalize the process of generating a digital signature, okay? I have a message, and this message says, hello world, or something sensitive. Maybe I wrote down my password, and I'm sending it to someone, saying, hey, this is the password to whatever. I'm going to take that message, and I'm going to put it into a hash function. Hash function, does anyone want to give me a description for a hash function? No brave souls? Yeah. Cool. Yeah. So generating unique IDs from arbitrary lengths of data. Pretty great description there. So we're going to take this message, we're going to put it into a hash function, so we get this random ID signifying, this is the data that it goes with. And then we're going to encrypt that ID with some encryption key. And this will then form this encrypted hash. It'll look like a bunch of random bytes that we won't actually know what they are. And so now, anyone who has this encryption key can run this backwards, right? They can take the encrypted hash, and then they can work their way backwards all the way to the hash function. Hash functions are inherently one way. You can't go from a hash to the message, but we can meet it in the middle by hashing the message and then decrypting the encrypted hash using the key, and we kind of meet in the middle and compare notes and check that they actually line up. So in reality, this is what we called an HMAC. So it stands for a hash message authentication code. So we can calculate the authenticity of messages. And so, store that one in the brain for later as well. Whenever you see HMAC, that's what you're looking at. So Now, when we want to send a message, we have our message and we have our HMAC. So this is how we can send a message and someone can then verify that not only am I, not necessarily me, but not someone who has the encryption key sent this message, but also the message wasn't messed with in transit. The problem with this is that we are going to now have to send this key to every single person who needs to communicate. And if I send this key to this entire table in front of me, and all 4 of you have access to this key, and one of you sends me a message, how do I know which one of the 4 of you sent it? So this is where we start to use what's called public and private key pairs. Public and private key pairs are different because instead of one single key, like a password or something like that, they use 2 separate keys that can verify each other's signatures. So if I encrypt something with a public key, the only thing that can decrypt it is the private key. It's a bunch of fancy math. Go take a crypto course. You'll understand. You'll be forced to do it by hand. It's really annoying, but honestly, it's really cool to see how it works on the inside. So let's send a secure message. So this person is now going to send their public key for use later on. We can distribute this publicly on the internet. It's okay because we want one half of this key pair to be public. Then we're going to take the message, we're going to sign it with the private key instead of the generic key we were using before. We're going to sign this with the private key. So now that gives us this this key pair, or this message and HMAC. So now, in the event that we have a bad actor in the middle, someone who's intercepting our messages or trying to forge our messages, if they modify the message itself, you can see now the message is tainted because it's red. Sorry if you're colorblind. Is anyone colorblind in the room? So I have to call that out. All right, I will make sure to explicitly note that. I didn't think about that when I was making this. So now this message is tainted, right? It's been modified. But they can't modify the encrypted hash. That's something they can't do because they don't have the private key. So now when we receive this bad message, we can do what we were doing before, work it backwards. So we can take the message, generate a hash, which will generate this red hash on top, which is a bad hash. We can go on the bottom, we can use the public key to decrypt that encrypted HMAC. And that will give us this original hash. And now we can compare notes. We can see that they don't match because they don't match colors, obviously. And so we can discard this message because it's invalid. The signature is invalid, and we know that it's not authentic. Switching gears one last time, I promise this is the end of the background section. TPM, does anyone know what it is? First, does anyone know what it stands for? Trusted Platform Module. Great, cool. Does anyone have a brief description of it? A backdoor from the government. Wow, thanks. All right. Yeah, so TPM's something you've probably heard of if you've ever had to upgrade from Windows 10 to Windows 11. It's probably shown up on your screen at some point. But they're these funky little modules. Historically, they've looked like this because this top left image, because they've been pluggable into like computer motherboards. They haven't been a component that has lived on a motherboard historically. So that's why during the Windows 10 to Windows 11 upgrade, it was super important to check that your device had a TPM because Windows 11 requires this. So if you had a motherboard that didn't have one, you would then have to go purchase one of these modules. I think they're like $30 or something like that, and then you plug them into your motherboard. But what these are is an integrated circuit that's tamper resistant because you'd have to physically take apart the IC itself, which is that little tiny, the little tiny like square above the connector itself. But yeah, so this implements cryptographic operations in hardware. So there is no, I guess technically the software is programmed. It's an ASIC. So things like key generation and signing data happen in hardware on the TPM. It can also store cryptographic keys and limited flash memory on board. But this, calling back to earlier, is the root of trust of our computer. So this is the thing that we inherently trust that, everyone in our context, us, because we're the only users of our computer, but everyone using our computer trusts the TPM to do its job and not be tampered with. All right, getting into the meat of the project itself. So online payments, you go to Amazon.com, you place an order for, I don't know, whatever you're interested in. I'm not going to judge. But the traditional, payment flow system of when you actually create a transaction, there are three main elements. So it's going to be the bank, what we're going to call the merchant server. So this is like Amazon.com. This is whatever you're purchasing through, as well as your browser. And so a traditional payment flow is going to, require you to enter in your payment details, your credit card number, all that jazz. I'm sure you've done it before. And then that server is going to attempt a transaction with your bank. Your bank is going to approve or deny your transaction. No, I will note that for the purposes of this presentation, I did simplify it. There are technically two separate entities, the bank and a merchant, which is confusing, which is why I combined them. The merchant is your payment card network. So, not your merchant. It is your payment card network. So it's things like Visa, MasterCard, these kinds of things that even if you get a debit card from your bank, you're going to see something on there that says it's a Visa, a MasterCard. There's a bunch of them. Discover. There's a bunch of European and Asian Pacific ones as well. So we kind of ignore them for the purpose of this presentation. But your bank will then approve or deny this transaction and then send the result back to the server, and eventually you'll see feedback on your browser. So this is how it typically works. Now, the verification of these card details happens at the bank, and solely the bank, right? We don't trust Amazon.com to verify your credit card details, but whoever actually verifies that the owner consented to this transaction. Now, if I gave you my credit card, you could then go and make a purchase because in this model, my bank never actually checks that I intended to make this transaction. Plus, now your credit card details have hit three separate systems, right? Your credit card details have gone through your browser, through Amazon.com, all the way to your bank, and your credit card details now live in all these places, in theory. So, this presents a lot of problems, right? There's high risk of, capturing these credential details. I know we talk about implementing HTTPS, well, not really SSL anymore, but TLS, and this is supposed to secure these things. But in when you're talking in context of trusted computing environment, you have to assume the entire environment is compromised, including your TLS connection. So we need to be able to validate that a transaction was actually started by the person who owns the card, which is super important. Because, your physical card can be stolen, or I can lend it to you and you can do something with it. Or, a database, historically very big, databases can be leaked. Now we address these things with like PCI DSS and kind of these governance and auditing, but it doesn't catch everything, right? You're also vulnerable to phishing attacks. Fraud through this system is super big. So how do we make these more secure? So a big thing is implementing like multi-factor authentication. We have it everywhere. It's huge. So we're gonna only address the kind of left side of our original model here, where the browser still operates the same way. But once we hit the bank, before verifying the actual transaction, or before like sending the result back to the server, it's first going to send you a multi-factor authentication request. This can come in the form of an email, a text message, a phone call, giving you a PIN number or something like that to verify. Maybe it's a yes/no push notification on your banking app, and your bank will then process it as normal once you approve. But it is important to note that this verification, relies on like other technologies to secure. There's no actual cryptographic verification that I'm the one who allowed this transaction. If you stole my phone while it was unlocked, and you could press yes on this this push notification. So some of the existing work in the field is like 3D Secure. So this is a form of multi-factor authentication where you have security across 3 separate domains. It's going to be your acquirer, your issuer, and your interoperable domain between them. And this is kind of in that payment card network that I was talking about before. But this exists in the form of like little web pop-ups. You may have experienced this. I know it's not super common because most banks don't actually enforce this. It's merely a feature. But a little web pop-up might come up saying, log into your bank or enter a code that we just texted you. This is 3D Secure at work. Your Amazon.com is going to receive, hey, we need them to interact with this 3D Secure page, redirect their browser to this URL. They'll complete the action and get redirected back to the page with a confirmation. So this entire flow is controlled by your bank, and you know, it's completely up to your bank to implement this system. This relies on your browser properly handling the redirect. So if your browser has a vulnerability in that redirect system, and it's an opportunity for compromise. And you know, this is relying on trusting a lot of different technologies between the two. And honestly, it still relies on you inputting your credit card information by hand. Hello? Okay, there we go. So some other works is EMV-enabled cards. So most of you guys have probably, if you had a card that just had a swipe before, you now have the option for a chip and a tap. Those are EMV-enabled cards. And so this little chip on board is actually used to create cryptographically backed transactions. So it does a little cryptographic verification. There is a private key that exists inside that chip. It's microscopic, but there's a tiny computer in your credit card that when you plug it in, it will actually perform public-private key operations to secure random numbers to identify that, hey, this is the card and this is someone who, you know, someone is actually physically plugging in this card. There's a lot that goes, you know, into it. But sometimes, you know, if to add an additional factor of authentication, it'll request you to type in a PIN or maybe your zip code for credit cards. And then both the card and the bank have to agree that this transaction is okay. So there's a kind of a two-way like distrust system. The card doesn't trust the bank, and the bank doesn't trust the card. So they both have to verify each other. And so this is super effective at reducing like multiple common types of physical card present attacks. But it only works in the physical domain. It only works when you have a physical transaction going on. Lastly, we have digital wallets. So these are things like Apple Pay, Google Pay, Samsung Pay, all these things in your phone. Sometimes I think there's like desktop versions that can support it now, but these are like dedicated apps or websites. Yeah, you can see it's integrated into like multiple other systems like WeChat, AliExpress has Alipay, PayPal, all these other different methods. They all exist in the form of this like digital wallet system. And this will authenticate you against whatever proprietary site you're using. So Google Pay will use your Google account, Apple Pay will use your Apple account, and so on. And these transactions oftentimes actually occur over a proprietary network. So let's say PayPal, for example. All of the transactions are actually being handled within PayPal itself. Nothing actually hits your bank until you have to draw money in or out of your PayPal wallet. So, you know, these are super easy to use, which makes them really common, especially outside the United States. I know in the United States, we rely heavily on our banking system. But outside the United States, this is super common for transferring money, paying for things, etc. But, you know, this provides very little interoperability. There's no, like, common thread between all these. They're all their own proprietary environment. So TrustedPay is this system that myself, and I forgot to call out at the beginning that Alex Beaver is also on this project last semester. Um, Together, we designed this kind of protocol called TrustedPay, and we're gonna go through the design now. So, when we set out to do this project, we had some goals. We wanted full cryptographic verification of online transactions. We wanted to protect against replay attacks. So if you just capture some network packets, whatever, an HTTP request and replay it, it's not going to work. And we also wanted to make sure that all devices using this were authorized to make transactions, such that if you stole my credit card, you couldn't immediately use it on your phone without my explicit consent. And so we made one big assumption, and that's that all network communications are secure. And if you're not familiar with security research, you develop a threat model for your application. And threat models have to make assumptions, because there is no way in the world of security research that you can end up securing every single layer of your entire design. And so, network protocols are way outside of the scope of what we're doing. We're developing an application layer protocol. So if this is new to you, we assume, based on all other research in the area, that network communications are going to be secure. And if they are not, that's outside of the scope of the project. So our solution to this problem is to use TPMs to sign our online transactions. So here's the modified payment flow. We have an additional element in our traditional payment flow, and this is what we call the TrustedPay terminal. And terminal is a word commonly used to refer to the thing that you tap your card or plug your card into. But in this case, it's actually software running on your computer. Oh, I forgot to update the colors in this one. Sorry for the flashbang there. So this payment flow exists in 3 separate stages. So first, your browser is going to initiate that transaction. And your bank is going to generate something called a nonce. Does anyone know what a nonce is? Number only used once. Perfect. So this is a random number that's used once and then discarded. Perfect. So your bank is going to generate this random number. Only your bank knows, and only your browser can receive it. That's the whole purpose of assuming all network communications are secure. So your browser receives this nonce, and then it contacts the TrustedPay terminal through an API and says, hey, sign this transaction. I'm trying to make this transaction. Here's what I'm sending to Amazon.com, and here's a nonce that your bank provided to validate this transaction. It will use TPM to actually generate that signature and send it back to your bank, who will then verify that signature during the authorization phase. And then, of course, like normal, it'll provide feedback to the server and your browser saying, yeah, transaction was good or transaction denied. Again, if you've never done security research, this may also be new to you, but this is a message sequence diagram or a message sequence chart. So really what this is this just formalizes what I just described in the last slide. But it shows the different communications and what data is passed in each step. There is a full paper that is linked, I think, on the GitHub that you can read that includes more about this. But the high level here is that the user is going to initiate the transaction by entering the card details. The merchant will then get a nonce from your bank. The browser will receive that nonce, and it will get a signature from TrustedPay. I think I've already reviewed this, but the terminal will then sign that transaction with the key, which is actually pre-authorized, which is super important. You have to pre-authorize this device to make transactions, like I alluded to earlier. And then the bank will validate this signature using all of its known registered keys, and it will provide that feedback. Some of the primary challenges when creating this design is that designing an entire protocol yourself takes a really long time, and making it work And also, you have to make this super efficient and simple, not only for banks and software engineers to implement, but also for the end user to use. If it's not easily usable, people aren't going to use it because security is annoying. This is one of my things I always say. Security is really annoying in the end of the day. It gets in the way. But we also, we evaluated TPM as well as trust zone backed solutions. Trust zone, obviously, way outside of the scope of this presentation, but highly recommend it if you're interested in trusted computing and you're interested in the ARM architecture. Go take a look at Trust Zone. It's a really cool thing, really cool technology. So some of the lessons that we learned is that even just adding and utilizing TPM alone can solve a lot of the trusted computing challenges. Trusted execution environments, which is what we call Trust Zone, didn't really allude to it, not necessarily easy to explain within the scope of this presentation, but they're not needed, and we can simply solve with TPMs alone. International sorry, I'm reading my notes wrong. Intentional system and application design can greatly reduce system complexity. Instead of developing these systems in silos, developing one system and then saying, hey, you got to develop your system to interact with my system. Let's just go ahead and think about the overall picture, and let's try and intentionally design our systems to be interoperable and reduce that complexity. And a requirement of 3D Secure is that there should be no additional software installed on a user's laptop. This whole thing operates out of the user's browser. But this adds significant complexity and security risk as previously identified. So there's a little demo. I'm going to give you a highlight of what to look out for. It is a video, so that way we don't have to worry about live demos. But in the top left, there's going to be 3 terminals. Terminal, no GUI, sorry. But there, in the top left, there's going to be the TrustedPay terminal. This is going to sign transactions using the keys that are stored on the TPM. We're emulating the TPM in this case. On the bottom, there's going to be what we call example e-commerce. This kind of merges the browser and the server because it's irrelevant. In the top right, we're also going to have the bank. Hello? All right, there we go. So as you can see, it generates a public key that we can then pre-authorize in our bank. All right. And as soon as we try and initiate a transaction, the bank will actually validate the signature of that transaction and approve it. And I think, how many times do I do this? Hello? Okay, I guess I didn't show it in that video. But the idea is that eventually, if you were to regenerate that key, the transactions would no longer be valid. So, some obvious additions that can be made, implementing PIN-based credential decryption on the terminal. So every time you want to sign a transaction using Windows Hello or other technologies, to simply just validate via a password that you want to use this. You can also password protect cryptographic keys as well in using TPM. Remote attestation of the actual software, ensuring that the software wasn't modified or injected into with malware. And then also like Trust Zone integration for ARM devices such as your cell phone. So there's plenty of opportunity for addition. We open sourced it all. There was a QR code at the beginning. Sorry if you didn't get to see that. But if you just look up TrustedPay on GitHub, you can see all of our work. Here's all of our academic references. If you're not a big research person, probably don't look at these. These are really technically dense papers. Yeah, that's it. Any questions? The question is this something we're looking to get published as a paper? The answer is probably no. I don't have the time or bandwidth to, get this into a published state. Maybe in the future, but not right now. Another question? So this project was actually designed for the research seminar Trusted Computing class. You're tasked with a semester-long project about something in trusted computing, and so we found that a very common area of security risk is our payment systems and our payment networks. And we realized that all these technologies are being put in place to protect physical transactions like the EMV chip cards, Apple Pay, trying to push these kinds of things. But people still rely today on just entering their credit card details into a website. And that CVV code on the back is supposed to solve that, but it's a 3-digit number. You can brute force that in, I don't know, less than a second probably. I don't know if anyone knows that off the top of their head, but you can probably just brute force that in like less than a second. So, it's really insecure, and we need cryptographic verification of these actually of the not only the transaction details, but the user consenting to the transaction. Any other last questions? Yeah, so the question was, is two-factor authentication or multi-factor authentication trying to solve the same problem? And at its core, I would say yes. The whole design behind MFA is intention, right? Capturing that intention, because the password is something we know, and maybe we have to prove it with something we have, like a security key. But um, there, or an MFA prompt. But the combination of those, the more factors you add, the more intention you kind of prove. If an attacker just has your password and not your MFA, push notification, then it's really hard to prove that the attacker is you and you're intending to log in. If you have 3 factors, there's additional, exponential difficulty in trying to prove that intention. So there are like flaws in both, right? Where it's only one element of a larger system. So the way we envision this working is integrated with other MFA systems. It adds another layer on top of that, increasing the difficulty exponentially. We don't see this as a solution that exists purely by itself. Yeah. Yeah, so the question was like, instead of a duo push, the device's TPM would be authorizing it. And I think the answer to that is both. Your device would not only sign the transaction before it leaves your computer, but then at the bank, it would trigger all additional multi-factor requirements. So TrustedPay would be one of those requirements. It would, satisfy one factor of authentication, but you still have additional factors of authentication required, such as text message, push notification, that kind of stuff. Yeah, it's another avenue for adding on top of additional security onto this multi-factor authentication system. Yeah, so the question is remote registration and deregistration for devices. So the registration process that you saw in the demo was you simply had to, copy paste this public key. So what we kind of envisioned is this maybe a browser extension or something that would connect to the software. Um, and then when you visit your bank's website and you initialize this technology, it would create a key, transfer it to your bank. Your bank would then say, all right, your device is now pre-authorized. So at any time, you could then log into your bank and revoke that authority that it has, similar to how I'm sure a bunch of you have like GitHub authorized keys on there. At any time, you can log into your account, you can click delete on the key, and the next time you try and access GitHub with that SSH key, it won't work. So similar system to that. Similar, yeah, similar to SSH, how you have like a list of authorized keys and that kind of stuff. Cool. Thank you very much.